All right, thanks everyone for joining us today. This is the second panel this year on our Digital Manufacturing Cybersecurity series. Hopefully everyone can see my screen comfortably. What I wanted to cover today is I'm going to be briefly introducing our guests, our moderator, Michael, and then he is going to be taking over our series. So let me just briefly introduce what we're talking about today. Today's panel is the second in the 2022 series. This is the third year that we've been running the panels, and we're going to be talking about the directions and future of manufacturing in digital manufacturing cybersecurity. This is a very interesting area with regards to the cybersecurity of manufacturing as we're changing and as the future of new manufacturing directions come in with regards to smart hybrid manufacturing, additive manufacturing. We're seeing more and more computer control and new manufacturing processes that are not only, revolutionary with regards to the kinds of parts that we can manufacture, the methods of parts that we can manufacture, but also the tools and techniques that are coming into this that have new intellectual property value, new methods of computation, such as machine learning based things, and also as a result of that, potentially new ways for people to try and work maliciously in this space. So that could involve trying to steal intellectual property or, trying to perform sabotage of attacks or anything like that. So to hand over to this discussion, we've got 4 really eminent panelists today, as you can see on the screen at the moment. I'm going to get Michael Bourque, who's our moderator. He's the Director of Digital Manufacturing for Boston Engineering, and he's going to be handling the discussion today. Now, this is an interactive discussion. This is your chance to ask questions of these industry professionals. And so for members in the audience, I really encourage you use the Zoom Q&A features to make sure that you to put your own questions in and so that these panelists can answer them. So without too much further ado, let me hand over to Michael, who is going to introduce the rest of the panelists. Thanks very much, Michael. I have got some other screen slides that Michael has kindly given me to share, so I'm now going to share those. Screen, here we go. Okay.
All right, well, this is where I take over.
Yes,
thank you,
thanks
Hammond.
very much, Michael.
Thank you very much. It's really a pleasure to be here. It's my second time here. A little bit about myself. I have a vast background in industry, manufacturing, all the way through automation and robotics. I started as a machinist, programming CNC machines. I was very fortunate to get a job at MIT, where I did a lot of research on machine tools, machine tool technology, subtractive machining. You could advance to the next slide. And then eventually I started getting into developing software for the industry. So I worked at PTC, which is a company that builds software, CAD CAM systems and that sort of stuff that drive 3D printers and designs. I was a vice president when I left PTC. It was a $1.3 billion company. Today, and then I started a company. You can go to the next slide. I started a company of my own. Where I bought a 3D printer and I did all the design and engineering, and I brought this product to market and raised $7.5 million on a 3D printed prototype. And then I worked for Stratasys. Stratasys is a company that makes pretty much invented 3D printing 32 years ago, and I was the director of all the product definition and product development that was going on in the software realm of the software for the machines as well as the firmware. Again, it's really a pleasure to be here. I wanted you to know that I went to a trade school and that I know what it's like to make things. I still love making things. I've got a 3D printer in my basement, and it's a delight to be able to meet today's panel and the topic, actually, because it's actually quite interesting. So with that, I'm going to introduce everybody. So our first panelist is Don Jones, executive in residence from Carlisle and Company. Don Jones has specialized expertise in 3D printing and impact on global parts logistics and led aftermarket parts. He has published articles on application of 3D in Wall Street Journal and aggregate research, and spoken at several additive conferences, including keynotes at Rapid TCT and the Edison Awards. Don holds a BA in management from the University of Illinois and MS in International Logistics and Supply Chain Strategy from the Georgia Institute of Technology. Don is currently the executive in residence at Carlisle and Company and the director of business development at Alloy Enterprises. So it's really a pleasure to have you here, Don. Don, wave your hand if you can, so everybody knows who you are.
All right, I'm sorry I was muted. Yeah, thank you very much. Great to be here this morning.
Don's the one with the red tie. Secondly, we have Dr. Mahdi Javanmard, Associate Professor of Electrical and Computer Engineering from Rutgers University. Mahdi received a BS degree from the Georgia Institute of Technology in 2002 and has an MS and PhD degrees in electrical engineering from Stanford University in 2004 and 2008, respectively. During his time at Stanford, he worked on a development of electronic microfluid platforms for low-cost genomic and proteomic biomarker detection, and later worked as a senior research engineer with the Stanford Genome Technology Center. In the fall of 2014, he joined the Electrical and Computer Engineering Department, Rutgers University, as an assistant professor, and his research interests include developing portable and wearable technologies for the continuous health monitoring and understanding the effects of the environment on health. So it's really a pleasure to have you here, Mahdi. Please raise your hands.
Thanks, Michael. Pleasure to be here.
Really impressive background, amazing. And then finally, we have Dr. Brandon McWilliams. He's on the phone. We don't have him on video right now, but Dr. Brandon McWilliams, a metals additive manufacturing lead from DEVCOM, the Army Research Laboratory. Brandon is the technical lead for the metals additive manufacturing at DEVCOM Army Research Laboratory. He earned his PhD at material science from engineering at Drexel University in 2008. His research interests include multi-scale modeling and experimental validation at relevant length and timescales, constitutive modeling, process modeling, and virtual manufacturing, non-conventional field-based processing of materials, and additive manufacturing. Recently, research has focused on understanding processing, microsecurity, property, relations, and AM metals, developing in situ processes, monitoring technologies along with digital machine learning based analytic tools for powder bed AM processes, and developing integrated computational materials engineering approaches to AM feedstock material development to accelerate develop of new capabilities which address Army modernization practices. Boy, what an honor it is to have you here as well, Dr. Brandon. Very nice to meet you.
Thanks,
Please, yes, thank you. So I'm really pleased to have our panelists. It's amazing who we have here, and I want to quickly get started. But now I want to request that each panelist actually take us through a few minutes of their own words, what they're doing, what's interesting, what are they doing in the field, what are they thinking about, what do they think they're disrupting, why is this an important and exciting topic, why are you here? So I'll start with Don. If you could take us through a few of your stories and slides.
Yeah, great. Thanks, Michael. Appreciate it. So I want to focus today on aftermarket parts, especially around automotive, heavy equipment, power sports, aerospace. This is a huge business, multi-hundreds of billions for all the OEMs globally. It's critical to their brand image and how they support their customer base. And I want to talk a little about additive and how it's an enabler, but also a barrier remover for entry for the gray market. So if you look at the OEMs, additive brings benefits in a number of areas. So cost reduction, especially for most of these OEMs have very long-lived parts. They have a lot of slow-moving inventory, billions and hundreds of thousands of square feet, if not millions of square feet of warehouse space dedicated to holding these parts. And like I said, it's critical to the brand that they have parts in stock for slow movers. However, the ability to keep investing capital through part proliferation and then also hold the tooling is a big challenge. So additive gives them the ability to remove minimum order quantities or all-time buys from suppliers, take inventory out. You can print on demand, especially as the ability to print globally becomes and consistently becomes more in place. They can print closer to the point of use. The space required, like I mentioned, is enormous. So the ability to print on demand will help tremendously with that area. And with sustainability as well, because the slow moving parts are often not in the right place on the planet. There's a lot of expedited freight and a lot of that's air to get parts where they're needed. So there's a great CO2 win here by printing close to the point of need and eliminating transportation and scrap and raw materials and a lot of overpack that's needed for those long journeys. There's a ability to increase their sales and brand impact. Today, if a customer comes into a dealer and needs a part, they don't have it. It may take months to get the tooling done, may take a few more months to get the part and then post-processing. So the customer may leave. But if the OEMs could promise the part in a week or two, many customers would wait for the part, and there's a chance for some increased sales there. And then the real win for all these OEMs is design for 3D. Like I mentioned many times, the space required for a lot of assemblies requires a number of individual SKUs. They have to be then assembled, welded, bolted together, gaskets. There's a lot of leaks and loose problems with quality. So as design for 3D becomes embedded, they'll be able to print parts in one piece and eliminate a lot of warehouse storage space and quality problems. All these benefits are great for the OEM, but they also remove barriers to entry for their competitors. It's very easy to get a part, get a 3D scan of it, put it in your CAD system, clean up the drawing, and then print a part. So the OEMs need to guard against that. We'll talk about that in a second, how that relates to cybersecurity. Go ahead, please. So just very quickly, if you consider this problem statement and how additive is so important here going forward for both metals and polymers, consider this steering bracket. It's made out of aluminum. It has very low demand, maybe one a year, and there are 0 in stock. Tooling's been destroyed or the supplier may be out of business, but the OEM wants to fulfill this part for brand protection when it's been ordered. Original cost $70, suggested list maybe $150. Well, with traditional manufacturing on the right, the supplier might be located, have to create tooling, could cost, in this example, $18,000. In many cases, it's much more expensive. A minimum buy would be put in place. So you have this very big investment, plus the weighted average cost of capital over 30 years for the storage of the material you didn't really want, but you had to take the minimum buy. Maybe you can increase the price a little bit, but the max return is still a huge loss. And all the OEMs go through this every day, many times a day. But with additive, again, no tooling, get the part quickly, no MOQ, you can make them as ordered, that's minimum order quantity. You can get the market to accept a little bit higher price because it's an older part. Similar post-processing is required in both manufacturing methods, so that's basically a push. And then this new piece part cost is drastically lower, including the printer and environment and the feedstock and the technician to run it. So in this case, the OEM has actually a net return with no other residual costs. So this is the value prop and the game changer for all of these OEMs to employ additive. Go ahead, please. However, there are a number of issues here around cybersecurity and IP protection. There are a lot of threats that must be mitigated, print integrity to make sure the part actually printed as it was designed to print. Counterfeiting, there's a lot of work being done on embedding technologies to allow the counterfeit part to be identified, because the OEM part would have embedded technology to show that it was made by the OEM. The theft of the design of the build file is a big issue. There's a lot of encryption needed to secure the files, and the material specifications, the formula of the part, and actually the print method are all intellectual property that need to be protected as well. Just because you can print a part doesn't mean you knew the X, Y, and Z axis required to print the part in the right strength. So there's an IP around that must be protected with cybersecurity. And then there are the environment issues as well around the network itself, protecting files as they travel around the world on the encryption or on a private network, protecting the databases from hack, and then again, the printer setup. So these are all really big, important areas for all of these OEMs to be solved before additive will meet its potential. Go ahead, please. So in summary, just the base points here, these technologies will be ubiquitous over time. Plastics have been around a long time. All the OEMs that are in these spaces have used polymers for jigs and fixtures and assembly help on the manufacturing line. Metals are fairly new, and I have an example here. I've held it up as close as I can. This is a very complex part made out of 6061 aluminum. It's fully dense. It has no porosity in it. It's a new manufacturing method, but having OEMs understand that metals now can solve problems is a big change. However, they have to give engineers get their head around basically how to prove that this meets APQP and the requirements of the PPAP. So we need ISO to continue their work to issue new standards that allow you to check the form and fit and function of the part, and not necessarily how it was manufactured. So that'll be a big change for engineers to get this in place. Security, we talked about that. The security controls are mandatory and have to be in place before this goes into production and critical use. But every OEM should be exploring this now, either through their own additive factory or using a service bureau. There are many out there that could print some sample parts, get engineers on this journey, but don't be left behind. This is a critical area that has to be invested in right now. So those are my comments. I'll be happy to entertain any questions.
We're probably going to take some questions after some of the introductions. So really great topics here. So let's go on and have Mahdi slides, and let's hear what you're doing. What's interesting that you're doing out here, Mahdi?
Thanks, Michael. So hi, everybody. So I'm kind of coming at this problem from a different angle and a different background. Maybe I feel like I'm the odd one in the group, but I think that creates really interesting opportunities for collaboration at the interface of different fields. So essentially, my background is I'm more of a medical device researcher. My group develops solutions for building medical devices that can be used to diagnose diseases at early stages. And the approach we take is by looking at biomolecules in the body, that in the bloodstream and various bodily fluids like saliva, sweat, breath, and to see how these can be used as indicators of disease, how they can be used to signal disease or the state of the disease. We look at things like nucleic acids, proteins, metabolites, and cells. Next slide, please. Essentially, what we do is try to build really tiny technologies, microchips that can be used to analyze these. Next slide, with the goal of enabling precision medicine and personalized medicine. In other words, understanding the patient's condition at the molecular level to give a diagnosis, as opposed to the patient's outwardly symptom alone, which is really what the common practice is today. Next, please. So we're living in a world of wearables where we're accustomed to things like heart rate monitors, pulse oximeters, activity monitors, and all sorts of other devices that measure physical parameters. What my group's goal is to build technologies that are wearable, either worn on the body or wearable more loosely, in the sense that you can wear them, carry them around in your pocket and continuously monitor your health, but doing it at a more deeper level, at a physiological level, and combining that with the data that you're obtaining from physical wearable devices, understanding also what you're being exposed to and in the environment, and how those different parameters essentially are related to each other. And imagine, the possibilities that you can get from, this new paradigm that we like to call crowdsourced biomarker discovery. How you can develop new predictive algorithms and comprehensive history when you're obtaining billions of data points from millions of individuals. Next, please. So what does this have to do with security, right? So imagine, you have all these different types of medical devices, some that are monitoring your health, but also some that are actually implanted inside your body, and, the interaction going on between the two. As you can imagine, this is like a perfect grounds for either attacks, right, malicious attacks, or even eavesdropping. So medical device security is, as you can imagine, becoming extremely more important. Even as you may know, former Vice President Dick Cheney, he even has deactivated wireless access to his pacemaker. Just to give you an idea. So with collaborators here at Rutgers, we've looked at different things, right? How can you make medical devices more secure? For example, by protecting the information from potential eavesdroppers. So we've looked at hardware level, sensor level techniques in order to encrypt the data that's coming from devices. Like over here, you can see like a cytometer. This is a device that counts and quantifies, cellular levels inside your blood that can be used to diagnose different types of devices. How do you encrypt, for example, the data that's coming in from these cytometers to protect them from eavesdropping? Next slide. And so, another area that we've worked on is how, not just the protecting the information, but how do you ensure that the materials that you're using in these biosensors, which you could be manufacturing using additive manufacturing, how do you ensure that these are structurally sound materials that do indeed what they are supposed to, that hold up to the the different environments, that there's not malicious attacks being performed here. And as you can imagine, manufacturing is a huge part of my research. Additive manufacturing is becoming more and more prevalent in the medical device world. Next slide. So one of the things that we worked on to try to address this problem is when imagine you're working with a foundry that you may not have physical access to. How do you ensure that the device that you have 3D printed, the model that you've 3D printed is indeed the exact same design that you have provided to the manufacturer, right? How do you know there's not a malicious third-party attacker that's come in and tampered with the design to somehow make it structurally unsafe? And this can be used for medical devices, but as things like homes, buildings, and all sorts of other new applications and use cases are emerging from 3D printer, as you can imagine, this is a generalizable problem. So what we did was we came up with sort of a material science cyber/cyber-physical systems approach to tackling this problem. The approach we took was to take filament that's barcoded in a very specific way that you have knowledge of, with particles that can be imaged using various spectroscopic techniques like Raman spectroscopy or near infrared spectroscopy. Have these barcodes at specific points in the filament, so that when you 3D print the 3D model, those barcodes end up in the right places, and then with some sort of a 3D imaging system, you can inspect and ensure that the device you fabricated is manufactured is what you wanted. So this is just a flavor of some of the problems that my team and my collaborators are working on. So I think I'll stop there.
Yeah, wow, that's really incredible. You paint a really great future. The thought of wearing a device that's checking on you every day, I just had this thought, it's like seeing the doctor every day. Imagine if you could see your doctor every day and they're measuring all this kind of stuff. So that's a great invention, but it's not going to be any good unless people embrace it. And there's that security dystopian problem that you talk about. And then also what you're talking about is ways to prove authenticity is really interesting. Thank you, Mahdi. Really great topic. Also, I want to also give Brandon a chance to tell us about what he's doing. in metals and research and the government. So please tell us about what you're doing, Brandon.
Thanks, Michael. I can't see the slides, so I'm going to rely on whoever's controlling it.
We'll figure it out.
Yeah.
Yeah.
Go straight to the second slide. Yeah, thanks for the opportunity to tell everybody a little bit about what we got going on at the Army Research Laboratory, and how we're using additive manufacturing as a tool to enable modernization. So just one quick, management type slide. What does the Army Research Lab do? So our mission is really to create and exploit scientific knowledge for transformational overmatch. So we always want to have the technological edge over our adversaries and have the latest and greatest in the hands of our soldiers. So next slide, please. So additive manufacturing is one tool that we see as kind of a next generation technology that we're using to achieve our goals. So in the middle pillar there, the two main priorities for the Army are sustainment, so maintaining our current platforms, a lot of which are very old, and there can be a lot of logistics issues with keeping those things running. And then the second goal, which is our kind of primary mission since we're part of the Army Futures Command, is modernization. So this slide, the two main gaps that we're addressing internally here are materials design, so coming up with specific alloys or feedstocks for a variety of different processes to meet Army objectives, and then tools for real-time qualification and certification. So I don't have this on here to try and say that the Army is going to solve this problem, but where there are specific tools, specific challenges where we can help the community along, that's our goal. So the banner at the bottom there, really this requires teaming, Army, academia, and it really should say DoD, not just Army, but DoD, academia, and industry to drive this forward, because it's a rapidly growing industry and community. So the slide says metals and alloys on it, so that's my personal bias. Really these materials and qualification challenges span the breadth of AM, material types and processes. And we have some efforts going on all that. So next slide, please. This is an example of how the Army is using additive manufacturing for modernization. This is our Science of Additive Manufacturing Next Generation Munitions program. And really, the goal here is to take all these different additive manufacturing technologies and converge them to get synergistic effects to push next generation kind of munitions, which is kind of the demonstration article here, forward. So pulling from hybrid AM, which we're using hybrid to describe things using multiple processes, so things like printed electronics, things like that, specifically for high G survivability, so very impact resistant printed electronics, design science, things like topological optimization, design for additive, metals additive manufacturing for different components in munitions to increase strength, increase range, things like that, as well as energetics AM, where we can actually print propellants, explosives, and all these are kind of separate right now. The goal is to eventually be able to print all these things concurrently in one kind of manufacturing process that combines all these different technologies. Next slide, please. I wanted to show, machine learning, I think, is a critical aspect. I think we've already heard it mentioned a few times here today. We do have some efforts going on there on using in situ monitoring tools to monitor these processes, looking at data analytics for a broad range of topics. So I think machine learning, machine vision, artificial intelligence, all these tools, there's a ton of different things you can do with additive manufacturing, from monitoring your process, from driving materials, design and development. So I'm a materials engineer by background, so that's one of my big interests. All these things can be driven by machine learning. It's a matter of generating the data. A lot of the in situ monitoring tools out there now are capable of generating tons and tons of data. We're starting to close the loop on how anomalies, how sensor signals, things that we can measure, correlate back to quality, both geometric quality as well as material property quality. Let's throw this up here as food for thought. Happy to discuss any of these things in more detail in a separate venue. Just wanted to give a quick snapshot of some of the things that we're focusing on with additive manufacturing at the Army. Thank you.
Wow, the Army is doing some really cool stuff. I just wrote down, I never heard of, wonder if anybody has ever heard of energetic AM. That's my first time hearing that. I guess that's printing rocket fuel or some propellant, right?
Yep. So things like propellants, explosives. Yeah.
So there would probably be some security around that. Must be important, right?
Yeah, for sure.
All right. So we've
Yeah,
met everybody. Oh, go ahead. You want to say something?
Yeah, so I think security, I didn't really talk about that because I figured we would
Right.
get into it with the question, but since we're jumping in.
Jump in.
Yeah, so DOS itself, which I think the other speaker talked about, ensuring what you get your print, but energetics in particular, protecting things like formulations and your materials is a key security aspect there, which I think is a little more unique to that space.
Okay, great. Well, I hope people are asking questions. Please, if you have a question, I think it's been mentioned, use the chat. We have a couple of questions that have been written in that I'll start everything off with, and the first one's going to go to Dawn. So Dawn, what are the current barriers for additive manufacturing and to become a preferred solution for OEMs and aftermarket parts and eventually new product design? Where are we going with all this? What are your thoughts?
Yeah, thanks. I think I touched on it a little bit, but the OEMs that I've worked with, it's getting engineers to understand that the additive technology is now viable. I'm not proposing that we go out and print, brake assemblies for a semi truck yet. I think we have a journey here, but let's try something. I know in my former life, we tried to print some grommets first, and no one cares about grommets unless you don't have them, and then you have to run a wire through a firewall. So we were able to print grommets, put them in production machines, and they didn't blow up, and they worked. So you kind of get engineers thinking about, well, maybe there is a new way to do things instead of injection molding. In that case, the metals, I think, is an enormous impact to these OEMs. So if we can get engineers to just try a bracket, do a tensile test, try a density cube, just to see that this material is real and viable now, and start the journey on how to get past the PPAP hurdle that's there now. I think the ISO standards will help a lot in that space. I think, it was materials, but I think the metal is now becoming quite good. I think more now it's trying to get the use cases in place. Thanks.
I met a company the other day I'd like to get your thoughts on, and what they're doing is they are making spare parts for cars that are no longer made anymore, and typically collector's cars. So if you've got a Maserati and you need a distributor cap, you can go to his website. He's reverse engineered it, printed it in a material that's safe for electricity, you would know. And I was amazed, because if you got a Maserati or a car that's not made anymore, here's a case where no one is making these parts anymore, but there is a market for people to get them printed on demand. And I asked him, does he print them on demand, or does he have 5 in stock at all the times? He actually just leaves 5 in stock and he gets more printed from a bureau. What are your thoughts on that? Have you ever heard of any use cases like that?
Yeah, actually, if you look at Jay Leno's Garage, there's different TV shows where they've done that for real out of production higher end vehicles that you just can't get any other way other than going to the expense of making the molding again, the molding tools. So yeah, there's that. Ford has some parts on the GT 500, I think, that are now actually 3D printed. So but it's all polymers so far. My knowledge is about polymers in that space. But the metals coming on now is a huge opportunity for these guys. But yeah, and also for vanity things. If you want your shift gear, in your Camaro to have your initials in it, you can print. You can have that printed in whatever color you want, and so there's an application there as well for customized things.
Well, let's go with some questions. I see we have a line of questions lined up, which is great. And let's see who wants to take these questions. Here's one. Can composites replace metals in the defense sector? Yeah, can composites actually, you know what? This is a very interesting question, because I think we're getting to a point where some of these plastic polymers that are reinforced are starting to rival metal. So that's the question I have for any of you. What do you think about that? And maybe this is for you, Brandon. It's the defense sector, but what do you think about this question?
Sure, I'll jump in with some thoughts. So I think composites, there's a lot of opportunity there. So you're starting to look at, high temperature materials, high strength, weight is a huge army for the Department of Defense. So I don't know about replacing metals, but I think there's definitely some niche applications where they're already being used. I think the use of composites has continued to grow. There's been a lot of advancements in manufacturing and quality control to assure uniformity and quality and things like that. So I think the use of composites has continued to grow, both fiber reinforced as well as other types of composites.
Yeah, something you mentioned about topology optimization, which is it's a fascinating topic I like to talk about. But yeah, instead of taking an existing thing that was made in metal and just producing in plastic, maybe there's a different way to design it so it performs its function and can be lightweight using topology optimization. What are your thoughts on that?
Yeah, absolutely. Topology optimization, you're starting to see that a lot more in industry where, a lot of companies are starting to use topology optimized parts. You save a lot of machining costs, or you can save a lot of machining costs where you're printing near net shape, even if you have to overbuild a little bit due to, uncertainty and things like that with some of these designs, you still can get a lot of advantages there.
There was one sector of the, oh, go ahead.
No, I'm just going to add in one thing that I think was mentioned is the carbon fiber infused types of nylon. Mark Forged has a printer that's pretty good at that. And just an idea for the folks on the line, and I'm sure it will apply to DoD as well, is maybe those materials could be used as an interim corrective action. It's not going to last 10 years like the metal part, but perhaps you could print it quickly out of a carbon fiber and get whatever piece of equipment it is up and running for a few months while you're waiting for the metal part to be made. So as we're on this journey, this interim corrective action instead of a permanent corrective action might be a way to get started as well.
Great. Well, let's keep moving along with questions. I love questions. Here's a very interesting one, I think. With the increase of automation and 3D printing, there can be an assumption for some people that there'll be less need for the workforce. What would be the impact on traditional mechanical or manufacturing engineers? Are we going to be out of a job? What are robots going to do to us? What is automation going to do to us? I bet all of you have a very passionate answer about this, but who wants to go first? Mahdi, okay, go ahead, Don. Go ahead, go for it.
The design still has to happen. Right? You still need engineers to do the CAD designs. The parts that are coming out, plastics are getting really good now where the finish is almost ready for the cabin. But metals still need to be post-processed. They still need to be polished in a lot of cases, taps, bores, all kinds of stuff done. But so you still need machinists as well to do that work. I think the high volume applications still remain in place. If you're producing 10,000 a month, 3D is not doing that yet. So I think this is a journey, but those core competencies are still going to be needed. You still need people that can make molds or injection molding. You still need castings. There are some neat technologies to 3D print sand now to produce castings without making molds. But I think those jobs are going to be in place for quite a while.
That's great to hear. I'm glad because I'm a big fan of vocational schools and making things yourself. It's a wonderful time to be alive and to be an innovator. Is there another good question? Thanks for that, Don. Another good question. This one's going to go right to Mahdi, I'm sure. And it's about medical devices and security. I love everything you said about being able to wear these devices. But what are your thoughts on the material quality? How much security should we be worried about this? What about material quality, as you mentioned? This ability to print a barcode as material I never heard of anything like that. That's really interesting. Tell me more about that. Tell us more about that topic.
I think material quality is absolutely critical, especially when you're approaching regulatory clearance of your medical device, doing verification and validation of your device, your manufacturing process, ISO, 13485 certification in your manufacturers. These things are all very critical. And actually, there's another question that somebody asked, which I think the question actually kind of has the answer to some of these questions, and that was a question asked by Michael McGrath about how the security controls that work for enterprise IT systems are often inappropriate for operational technology systems like additive manufacturing, and how can OT security needs be addressed, and where will the needed expertise come from outside of IT tech support? And I think the answer to all these questions are kind of related, and that is, I think this is going to result in a new class of careers, a new class of professionals. Maybe we can think of it as like domain specific IT tech support, as opposed to sort of one size fits all training applying to all IT sectors. I think we're going to be maybe having IT materials IT specialists focused on medical device industry. Maybe for the defense industry, it's going to be a different specialization in itself. And I think related to the question about robots taking over and careers, I think new jobs are going to be created where a lot of those skills may still from the previous jobs still may be applicable. But maybe by augmenting your people augmenting their expertise and knowledge to add in these other aspects, right? Like material scientists or manufacturers needing expertise in cybersecurity as well, or cybersecurity specialists needing expertise in materials as well. I think that's the direction that things could ultimately head in.
Something also I see in your story is, I'm just pretend for a moment that 3D printing has never been invented yet. None of us know about it. You couldn't be doing what you're doing. The fact that you have the affordance to have a printer that you can mess around with, and it gives you this ability to develop this great technology in this point of view, right?
Exactly.
That's my favorite thing about 3D printing and additive manufacturing, that really it's so affordable now. And one of the best things I ever did was buy a 3D printer. Okay, let's see, we have more questions here. Please continue to send us in some questions. Here's one. What about the legal issues which will arise due to AI and IoT, I think he means, or IoT-IN, that might be a thing. So what about legal issues which arise due to using these technologies like AI, machine learning, IoT, all that kind of stuff? Who wants to take that? Brandon, I'm gonna pick on you. Are there any legal things we need to worry about? Does the government worry about legal things? Maybe not.
Brandon, you may have muted yourself by accident.
He's talking passionately about it and we can't hear it, probably.
Is that better?
Yeah. Hey, what do you think? Can you answer this?
It's a big issue. There's not an answer for it yet. I think working on it. One of the big issues the government has. So if you look at our ground vehicles, for example, designed in maybe the 60s or 70s, really old systems. Some of that we own the technical data for. Some of it we don't. It's a big challenge. They're working that out now. I don't have an answer now. The short answer is yes, it's a problem. I think it's already a problem because we're already trying to make some of these parts that you can't exist. And even if there's not a company currently selling it now, you have to identify who still owns that IP. Sometimes we have government rights, then it's not an issue. But yeah, it's a big problem, and I don't have a good answer. So if there's any sharp minds out there that do have answers, I'd love to hear them.
Well, it sounds like as an industry, we need to tackle these things. I'm sure you guys are going to conferences and shows. I'd like to ask maybe before we close what those are that you're going to. But there's a very interesting question that came in I want to actually ask, and it's about sabotage and these kind of threats with fake products. I watched this video about this company that tries to fight fake product getting into the marketplace. It's very easy for an overseas manufacturer to sabotage a brand and so forth, fake brands. So what kind of threats should we be thinking about here? I mean, what do you think? What are your thoughts about preventing this or helping this with this issue, especially around biomedical devices? What's the intellectual threat? Mahdi, I'll
So,
pick on you. Oh,
yeah,
oh,
yeah,
just
sure. So I think going back to like the legal issues, and then I can maybe speak more for like the medical device, the diagnostics industry. I think liability is a huge issue, as you can imagine. If you have a product, for example, that has AI embedded into it, a diagnostic product, that actually requires its own separate, pathway for getting FDA regulatory clearance. Also your device needs to be HIPAA compliant. Authentication of your devices is huge, but during your process of medical device manufacturing and scale up of your device, having numerous controls for verification and validation is also a huge issue. And again, it all comes down to all of the liability associated with the medical device, right? Imagine it's a diagnostic device that you have a false negative test, right? False positive test. The liability associated with that. It's interesting, 3 years ago when I used to have this conversation, I talked to people about like test strips. Nobody knew what a test strip was. Nobody knew what a PCR test was. Now, because of the pandemic, my grandmother knows the difference between a PCR and a rapid.
that's good. Yeah.
So as you can imagine, with things like test strips, being able to manufacture them with high reliability, verify and validate each batch, that comes through. This is definitely a huge challenge.
Maybe there were some fake N95 masks that were going around that we were buying, right? Who knows?
Yeah.
Actually, this reminds me of the conversation I had with this company that's making distributor caps for Maseratis. I asked him, well, have you called Maserati and said that you make them now? And so when a customer calls Maserati, they can, get the business. He says, oh, no. If they learned that I was actually making these, they would not be happy. So that's kind of interesting. Maserati's not interested in making this stuff, but this guy is a business doing it. Why is that? That shouldn't be, I don't know, it should be, let people repair their own things. In fact, maybe Dawn, I thought you were going to bring this up, but one car company released the scan data or maybe the CAD data of their dashboard so that people who are DIYers and print things, they could print accessories for the car, and everyone went wild. And I actually think there's going to be a day, I hope, what you think about it is that makers of these products can maybe give away some of the CAD data, not all of it, but just so you can build off it. Maybe the future is people augmenting these products with their own.
Yeah, there's a lot of protection for the aftermarket. Most of these OEMs make most of their profit from the aftermarket. So there's a balance in there of being a good customer support company and also protecting your own revenue stream for those things. One of the things that we didn't really explore too much was the integrity of the files. I talked about it very briefly, but you can imagine, especially in aerospace, the ability for someone to hack a file, change the characteristics of the print of a strut, for example, where it prints, still looks normal, but it fails at 3 Gs instead of 7 Gs like the original design. So there's a lot of IP protection, the legal ramifications of that. We talked, Mahdi talked about liability. You have that same kind of liability in these products. It has to be ensured that the integrity of the part and the file is ensured before it goes out to a customer. The last piece is IP. Do you even have the right to print the part? It kind of goes to your Maserati example. But if the OEM wants to support their own machinery, yet a tier 1 supplier did the IP design on a part of the machine, the OEM may not have the right to print the part. So there's some legal work that has to be done there to maybe come to a revenue sharing model to support those older parts where the supplier doesn't want to mess with it, but they don't want to completely give up their IP. So maybe there's a way for everybody to get a win with that, but there's certainly some legal work that has to be done.
I thought of a way to maybe summarize and close here is that, no one ever says they love their security. Ooh, I just bought great security. I love it. It's so great. I love that my virus didn't come to me today. It's expectation, and what I want to maybe ask you all to think about and reflect on is just because there's security issues and known unknowns, let's not that stop us from innovating. Let's keep pushing and the envelope and solving these problems as they come. Because you know, I heard once someone tell me, "Oh, I'm against 3D printers." I said, "Why?" It's because they can print guns. You know, I'm sure you've all gotten that before, but you know, 3D printing is just a huge revelation and an innovation, and it's going to change everything. So let me just ask each of the panel, I'll go backwards this time, starting with Brandon, give some closing remarks on your thoughts for today's session and what you might want to let everybody know with some parting words.
Sure. Yeah. Just thanks again for having me here. I guess I'll just say, I mean, additive manufacturing is here. It is the future. It's already being used as an industrial tool. I think the uses, applications, and the technology is going to continue to grow. I really like your comment about let's address the challenges as they come. A lot of these challenges aren't new. I'd also like to add that, right? So a lot of manufacturing, especially like high-end aerospace stuff, where you're really, you know, the integrity of the part is really critical. It's already being done by CNC, you know, computer-controlled manufacturing now. So these issues aren't new. I think we just need to address them and kind of work our way through it. Thank you again.
Thank you, Brandon. Yeah, I mean, hearing what you're doing and sharing it with others is, I think, really important. Everyone's doing such amazing work, and we really should have a place, and maybe this is it, right, where we share what we're doing. So I love that. I'm going to definitely LinkedIn you and want to chat with you sometime about what you're doing in metals. Mahdi, give us some closing remarks. What are your thoughts on today, and what do you want to leave people with?
Yeah, I totally agree with Brandon. I think additive manufacturing is here to stay. I don't think you know, it's going to displace, you know, traditional, you know, injection molding and other, you know, traditional technologies. I think that has its own place. The way I like to see it is, I think this is going to, you know, just open up a whole new, you know, series of use cases and applications. Just to kind of throw a crazy one at you. Talking with you know, folks at NASA, we had a grant with them on building, you know, blood cell analyzers for monitoring space health of astronauts. What they're very interested in is, look, we're sending astronauts out into deep space missions, right? That could take like 6 to 12 months. What about, you know, can you make it so that these test strips that are being manufactured, that they can be recycled and 3D printed on the space mission, right? Instead of having to, because every little bit of space, you know, and weight that you're carrying on a space mission like that is super critical. So again, that's just something you can't do with traditional, you know, subtractive based manufacturing. I think, you know, that's just kind of scratching the surface. I think there's a whole plethora of things you can do. It's all about democratizing technologies, right? When you democratize technology, you know, you open up, you know, people are going to come up with new applications that even the inventors of the original technology didn't envision to begin with.
And that's what's so exciting about it. I mean, 3D printing in space, oh my gosh. Let's get a CNC machine in space. I also want to remark that I met a very young, he's a 7-year-old kid. He's born without a hand. And I met him and he bought a 3D printer, and I'm helping him design and 3D print his own hand. Wow. And boy, this kid is amazing. He's already taught himself to program. He knows all about 3D printers. And so it's just remarkable to see what people do with it. They don't know the rules. No one gives them, and if you're never told what not to do, you end up changing the world, right? Thank you, Mahdi. And then Dawn, I'm going to let you have the last word here. What are your thoughts? Leave us with something that we can be excited about for the next 20 years.
Yeah, thanks, Michael. Again, thanks to the panel as well. It was a great session. I appreciate being able to participate. I would just go back to try it. You know, you don't need to solve the world's biggest problem with 3D printing right now. Find something that's a real pain point that you just can't get any other way and try it. For the OEMs with their hat on, give the part away, give it to the customer and tell them, hey, look, I think this will work, and get you up and running and see what happens. If it fails at 500 hours, then you learn something. but the customer had their machine running for a while. So just try it. You don't need to go out and spend $1 million on a printer. There are plenty of service bureaus that can get you started and see where it goes. Thanks.
That is so true. Service bureaus make 3D printing so much more accessible. And I really liked one of you said something about it's really important not to just have the design file, but all the settings that went into printing it, the orientation, all that extra metadata.
Right.
That's really important. In fact, that's like the recipe of making this product, and to keep it secure is important. Well, I want to thank you, all of you, and I appreciated this being a part of this. I'm going to hand it back to you, Hammond, and you know, as I said, it's a great time to get into 3D printing and additive manufacturing. Don't be afraid of security. Help us, right? Let's move this along. Let's live in a new brave world where we have innovation and disruption happening, and we can actually have personalized medicine. We can have better parts being made for our military and armed forces, and we can make spare parts for cars. So Hammond, thank you. I'll pass it to you. I think we're on time, right? Am I good at keeping time?
Yeah, that was very good. Thank you very much, Michael, and thanks everyone to, you know, thanks all the other panelists as well for joining us today. These kinds of discussions, you know, we think are really valuable for, you know, extending what we're doing into the general community. So just in general, I'd also like to thank the panel's sponsors, the National Science Foundation and NYU Center for Cybersecurity, and the other organizers of these panels that you don't get to see when you're just coming into the audience. That's Professor Nikhil Gupta and Professor Ramesh Karri at the NYU Tandon School of Engineering, and also Gary Mack, who is a PhD candidate here as well. And so one final thanks very much to our panelists and our moderator. If you joined late, or you know you want to watch this again in future, we're going to be posting the link to our YouTube channel. And of course, 1 month from now, on the first Thursday of next month, we'll have our next panel. And hopefully we will see you all there again. So thanks very much, everyone. And thank you for joining today.
Thank you, Hammond. You deserve some credit too. You've done a lot of behind the work scenes organizing this. So all of us appreciate that. I can't wait to watch this later.
Thank you so much.
Thanks,
Bye, everybody.